So today we are going to be talking about maximum average power transfer. And so to facilitate that, I guess I need to ask you guys, did you cover maximum power transfer in DC circuits? Ron's nodding his head. Yes, you guys are nodding your head no. Which means it sounds like at a minimum you could use a review. Fair enough. So let's say that I had a DC circuit that I could represent by its Thevenin equivalent circuit. You guys remember what a Thevenin equivalent circuit is? Mildly. Okay. So in a Thevenin equivalent circuit, you've effectively condensed down your circuit into an electrically equivalent circuit that contains only a Thevenin voltage source in series with a Thevenin resistance. You could have also a Norton equivalent circuit, which is a Norton current source in parallel with a Thevenin resistance, and those two sources, the Thevenin equivalent circuit and the Norton equivalent circuit, have to be electrically equivalent to each other because they're electrically equivalent to the same larger circuit. So just as a thing, let's just do this here. So I have some Thevenin voltage in series with some Thevenin resistance. This is what's called a Thevenin equivalent circuit. So I put a G there instead of T. Where VTH is the open circuit voltage of the live network, and RTH is the resistance seen looking into the terminals of a dead network. Just so that we're all speaking the same language here, a live network means a network where all of our independent voltage and current sources are on, and a dead network means a network where all of our independent voltage and current sources are off. Okay, so just as a quick review type thing, let's say that I had the following network. So let's say here's a 3 amp source, an 8 ohm resistor, 4 ohm resistor, 6 ohm resistor, and here's our open circuit terminals that we're going to try to find our Thevenin voltage across. How do you guys think we would solve for this Thevenin voltage?
Replace the short. Then we need a replacement.
I disagree wholeheartedly. So the Thevenin voltage is the voltage drop across the 4 ohm resistor in parallel with the 6 ohm resistor, because it's literally the voltage labeled as the drop across those two resistors in parallel. So I would argue that for this particular circuit, we could just simply use Ohm's law, because we know a total of 3 amps is going to flow through that parallel resistance. So this would simply be 3 amps times 4 ohms in parallel with 6 ohms. So 24 over 10, 2.4 times 3. If I did my mental math correctly, this would be 7.2 volts. Okay. So to be explicitly clear here, because this is something that you're going to be doing fairly regularly throughout at least the classes that you have with me, and this is part of power analysis and all of that kind of stuff. And when you guys go out into industry, Thevenin voltage is always the open circuit voltage across our element of interest or terminals of interest, right? So effectively what we're doing here is we're seeing what voltage some load would see. So let me put, right, so we're removing the load. So I'm going to put a load resistor here, RL, and I'm going to scoot this stuff over here to the right for now. So we remove the load resistor RL because we don't want that to influence our calculation, okay? So we would open circuit the load resistor RL, which means we remove it from the circuit entirely, find the voltage drop across those open circuited set of terminals, and that is our Thevenin voltage, which we just found for this particular situation using nothing more than Ohm's law, because that was all that was required, right? Our Thevenin equivalent resistance would be found. So let's do that really quickly. I'm going to redraw my original circuit. So here's my 3 amp source. Eight ohm resistor, 4 ohm resistor. Here's 6 ohm resistor. So here's my network. Thevenin resistance is always found looking at a dead network, which means I turn off my current source. How do I turn off a current source? It's an open circuit. Absolutely right. So the person that said don't draw it is also correct. So our Thevenin resistance here, what would that be? Absolutely right. Why doesn't the 8 ohm resistor show up? Because it's not part of a closed current carrying path. Absolutely. So just 4 in parallel with 6. Or .4 ohms. Okay. So we also have an option of what's called a Norton equivalent circuit. Which this could be also connected to some load. Put an RL over here. Okay. Where I Norton is the short circuit current flowing in the live network, and RTH is still defined in exactly the same way as it was earlier. No change in it whatsoever. Okay. So for our circuit of interest that we were looking at a moment ago, here we have our 3 amp source, our 8 ohm resistor, think this was 4, 6. So we're going to replace our load resistor with a short circuit. And we're going to find the current flowing through the short circuit. Anybody have any thoughts on what that might be? Will it be the same thing as what? So Thevenin voltage can't be Norton current because voltage and current aren't the same thing. So I have a problem with that line of reasoning. So 4 and 6 ohms are resistances, which are also not a current. All right, so I have a short circuit that is in parallel with a 4 ohm resistor and in parallel with a 6 ohm resistor. So what does that mean to the 4 ohm resistor and the 6 ohm resistor? So when things are in parallel, their voltages are the same. Okay, so let's go from that. What's the voltage drop across the short circuit? None of the voltage. A short circuit has 0 voltage drop across it. Okay, so if there's no voltage drop across that short circuit, and that short circuit is in parallel with the 4 ohm resistor and the 6 ohm resistor, what's the voltage drop across the 4 ohm resistor and the 6 ohm resistor? None, no voltage. Okay, so there's no voltage drop across the 4 ohm resistor and the 6 ohm resistor. Okay, through the short. Exactly right. So the 4 ohm resistor and the 6 ohm resistor are not going to contribute really anything because they are bypassed by that short circuit. Okay, so as far as the short circuit is concerned, those 4 ohm resistors and the 4 ohm resistor and the 6 ohm resistor may as well be an open circuit, right? No current is going to flow through them. Can't because there's no voltage drop across them, right? Ohm's law tells us that if V is equal to 0, when R is some finite value, then I must also be 0 because V is equal to I times R. So we know that the 3 amps of current will flow through the 8 ohm resistor. It can't not flow through the 8 ohm resistor. They're connected in series. It sees the 4 ohm resistor, says no thank you. Sees the 6 ohm resistor, says nope. So all of that 3 amps has to flow through the short circuit. So our Norton current is just 3 amps. Now, all of these 3 quantities are related to each other. Our Thevenin voltage is simply equal to our Norton current times our Thevenin resistance. That's nothing more than Ohm's law, by the way, right? So let's verify that this is correct. So we could say that our Norton current is simply the ratio of our Thevenin voltage to our Thevenin resistance. Well, I found my Thevenin voltage to be 7.2 volts. I found my Thevenin resistance to be 2.4 ohms. What's 7.2 divided by 2.4? Probably 3. It is 3. So either we can find any of those quantities directly, or as long as we can find 2, we can figure out what the third one is just by using that Ohm's law relationship thing here. All right. That was an incredibly brief review of Thevenin and Norton equivalent circuits because it sounds like you guys have had it before, just maybe a bit rusty or whatever. We can apply those techniques to find the Thevenin voltage, Thevenin resistance, and Norton current for any linear network, and we're only going to be dealing with linear networks in this class and really all of your subsequent classes, at least dealing with electricity, at least the ones that I teach, because we don't really get into nonlinear circuit elements like diodes, transistors, and all of that kind of good stuff. So, all right, so background done. Now let's actually talk about maximum power transfer. So let's suppose that I have a network that could be expressed using its Thevenin equivalent circuit. So here's my Thevenin resistance. And then over here is my load resistance, RL. I'm going to call this voltage drop VL and this current IL. And I want to develop a relationship for the power that is absorbed by my load resistance RL. So the power absorbed by my load resistance RL will simply be the product of the voltage and the current. Well, I can find that voltage VL by simply applying voltage division to this simplified circuit. So that's going to look like my Thevenin voltage times RL divided by RTH plus RL. I can find my load current simply by doing Ohm's law. So that's going to be VTH divided by RTH plus RL. And when I substitute those two relationships in, I find that my power is given by the Thevenin voltage squared times RL divided by RTH plus RL squared. So what I'm going to do is I'm going to create a plot here. And on my vertical axis is going to be my power as a function of my load resistance. And my horizontal axis will just be my load resistance. And this power should look something, so power is a function of load resistance. The curve should look something like this. Where over here on the left-hand side, we have no power being absorbed by our load because it's when our load is effectively a short circuit, right? So if we know that there's no voltage drop across it, there can't be any power absorbed. Way over here on the right-hand side is when my load resistance is effectively infinitely large or an open circuit. Since there's no current flowing through our load, there can't be any power absorbed either, right? Well, here in the middle, there is some peak value, right? That occurs when maximum power transfer happens, okay? So what we need to figure out is what value of RL makes maximum power transfer occur. You guys remember this at all? No. Okay. So okay. Okay. Good. At least you acknowledge that. Okay. So realistically, what we would be doing is we would be maximizing this equation right here, right? Or we would figure out when that equation hits its maximum, right? You guys have had some calculus, I believe. So how do you find the maximum value of a function? Take the derivative of the function and set it equal to 0, right? So we would be taking the derivative with respect to RL of V Thevenin squared times RL over R Thev plus RL quantity squared. Take the derivative and set that equal to 0. I'm not going to make you guys suffer through applying the quotient rule and all that kind of crap like that. What we'll find out is that this function is at its maximum when our load resistance RL is equal to our Thevenin resistance RTH. So and if we allow RTH to be equal to RL, or really RL to be equal to RTH, and we plug that into our power equation, what we're going to wind up getting is that our maximum power in a DC circuit is simply the Thevenin voltage squared divided by the Thevenin resistance multiplied by a factor of 1/5. Hopefully this is vaguely familiar because we're going to use it in just a couple of moments because we are beyond DC circuit analysis in this class. We're supposed to have that effectively down pat. And so now we're worried about the AC side of things. So now let's talk about the AC side of maximum average power transfer. Okay. So let's say that we have an AC circuit where we have some Thevenin RMS voltage phasor. We now have some Thevenin impedance ZTH. And over here, we're going to have some load impedance, right? So exact same circuit as we had before, but now we're looking at things from an AC perspective. So instead of using pure resistances, we're dealing with impedances. We have an RMS phasor voltage because our voltage source is no longer a DC thing. We can find our RMS phasor voltage VL like so, our RMS phasor current IL like so. And because we are finding average power, the average power, if you recall, is just the real part of our phasor voltage times the complex conjugate of our phasor current. Well, that's going to look like the magnitude of our voltage times the magnitude of our current times the cosine of theta V minus theta I. This is not remotely a new relationship. This is one of the ones that we talked about when we were dealing with complex power. I'm not expecting us to remember or have to apply that. I just want to use this to kind of see what shakes out of things. Okay? So yes, exactly right. So theta V is the phase angle of the RMS voltage phasor. Theta I is the phase angle of the RMS current phasor. So just as a heads up here, that thing right there is nothing more than theta S. The difference between theta V and theta I is just theta S. So all stuff that we arguably at least have seen before. Okay. So if I'm trying to find the power delivered to my load, I just need to find the magnitude of the voltage drop across my load, the magnitude of the current flowing through my load, and then the cosine of the difference in phase angles here, right? So the voltage drop across my load, we can find once again, just using voltage division. So that's going to be V Thevenin times ZL over ZTH plus ZL. Which I could write as VTH times RL plus JXL. All I'm doing is putting my impedance in rectangular form, divided by RTH plus RL plus JXTH plus XL. So I've just expressed my impedances in rectangular form, and then I added the real parts together and I added the imaginary parts together in the denominator. So now what I need is the magnitude of this thing. Okay. So to find the magnitude of this might blow your minds that it's this simple. I'm simply going to take the magnitude of each constituent part because they're all complex numbers and then multiply things together, right? So what I mean by that specifically is the magnitude of the Thevenin voltage is just literally the magnitude of the Thevenin voltage, whatever that happens to be, right? The magnitude of RL plus JXL is going to be the square root of RL squared plus XL squared. And now I'm going to divide this by the magnitude of the denominator, which is just going to be RTH plus RL squared XTH plus XL squared. And that is the exact same thing that I would get if I went through all of the effort of multiplying this thing by its complex conjugate and effectively foiling everything out. So here's my magnitude of my voltage. My current can be determined using just Ohm's law. So I would have my Thevenin voltage divided by DTH plus ZL, which I could write as DTH over RTH plus RL plus J XTH plus XL. And then the magnitude of this is just going to be the magnitude of my Thevenin voltage divided by the square root of RTH plus RL squared plus XTH plus XL squared. All of that is under a square root sign. So what we've done thus far is we figured out what the magnitude of the voltage is. We figured out what the magnitude of the current is. And so now we need to figure out what cosine of theta v minus theta I is going to be. Okay. This is going to maybe seem a little bit wonky. Sure. So we're focused on what's going on with the load right here. Okay, so I want to draw something out for you guys. And I use another one of my graph things here. So this is my real axis. This is my imaginary axis. And let's say, just for the sake of argument, that this is my impedance ZL. Okay. It has a real part. That is RL. It has an imaginary part, which is XL. And it forms an angle with the positive real axis that is going to be theta Z. Now, we know from previous discussions that an impedance is simply the ratio of the voltage drop to the current, right? Doesn't matter if we use an RMS phasor or not, so I'm going to put in RMS phasors here because that's what we've been dealing with. Well, this would just be the magnitude of VL divided by the magnitude of IL with an angle of theta V minus theta I. So that theta V minus theta I there is just theta Z. So now I want us to look back at this graph I have here where I depicted my impedance ZL on a complex plane, and I want us to figure out what the cosine of that angle theta Z is going to be. Okay. So how many of you guys remember your 8th, 9th, 10th grade trig or whatever? Couple of people raising their hands. Great. So what's like the fundamental way to find the cosine of an angle with a right triangle? The SOHCAHTOA thing. All right. So we want the cosine part. So adjacent over the hypotenuse. Okay. So let's look at the hypotenuse here real quick. So that's our hypotenuse. So the magnitude of ZL is just going to be the square root of RL squared plus XL squared. What part's the adjacent? The real part, so just RL. So cosine of theta V minus theta I is just RL divided by the square root of RL squared plus XL squared. Just using good old high school trig. What I'm going to do now is I'm just going to put all three of those parts together. Okay, so the magnitude of my voltage, the magnitude of my current, as well as the cosine of theta V minus theta I. And so what I wind up finding is that the average power absorbed by my load. So I'm going to put VL in first. So that's the magnitude of VTH times the square root of RL squared plus XL squared divided by the square root of RL squared plus RTH. Sorry, there shouldn't have been a squared here. There should be a squared outside. All of that is under a square root. So that's VL. IL is the magnitude of VTH. And lastly, I'm going to substitute in my cosine. Okay. So I just substituted in the three parts that we came up with. And I can see, bless you, that a couple of things wind up canceling each other out. So for instance, I have this square root of RL squared plus XL squared here in the numerator, same term in the denominator from my cosine term. Those guys go away. That big ugly denominator thing is the same for the VL term and the IL term. So that square root is going to go away because when I square the square root, that goes away. And so what I'm left with is the magnitude of my Thevenin voltage squared times RL divided by, let me put it like this, RTH plus RL squared XTH plus XL squared. So we did a whole bunch of work to figure out that this is the thing we are trying to maximize, okay? So I'm going to ask you guys an odd question, but what does our reactance do in terms of our average power here? It makes it smaller, right? So the reactance only shows up in the denominator. So if the quantity XTH plus XL is anything but zero, our average power is smaller than its maximum possible value. So that's our first constraint for figuring out what condition causes maximum average power transfer to occur. We need for our reactance to be zero. XTH is fixed. So that means that XL must be equal to negative XTH in order for that part to cancel out, right? So our first constraint is in order for maximum average power transfer to occur, XL must be equal to negative XTH. That triple equal sign instead of the normal double equal sign means like we force this to happen. So under that constraint, I'm going to call this PL prime, meaning we've already just done one step. Okay. We would have VTH magnitude squared times RL over RTH plus RL squared. So, because I want the reactance to be zero. If the reactance is anything other than zero, since it's in the denominator, it's going to make the average power smaller. Right? So let's say, just so we're all on the same page here, that RTH plus RL is 5 and XTH plus XL were 3, right? So I would have something over 25 plus 9, okay? Now let's say that I had that same something over 25 plus 0. Which of these numbers is bigger? The one on the right. So that's why we need to get rid of that reactance. And the only way that that happens is if our load reactance cancels out our Thevenin reactance. Effectively, yes. So in order for maximum average power transfer to occur, we need the reactances to cancel out, or we need it to look like a purely resistive thing. 100% correct, Brown. That will indeed cause maximum average power transfer to occur. Well, having a power factor of 1 will be a consequence of having maximum average power transfer over time. But just because our power factor is 1 doesn't mean that average power transfer or maximum average power transfer is occurring. And what I mean by that very specifically is we're about to find that there's a constraint on the value of the resistance as well. So we have this expression right here where we're trying to maximize or figure out what value of RL causes this expression to give us maximum average power transfer. So we have voltage squared times RL over RTH plus RL quantity squared. Anybody have any thoughts on how we might maximize this thing, Brock? It is. The prime right here is just denoting that I've already canceled out my reactance. It is not the derivative. As a matter of fact, and I want to clarify this here, I will never, ever, ever use a prime designation to denote a derivative, double prime as second derivative, or anything like that. If I want you guys to take a derivative, I will literally say d by d, whatever variable you're taking the derivative with respect to. So we are trying to figure out what value of RL maximizes this expression. What was that? It's literally the exact same expression that we were maximizing in a DC circuit. The result of which was maximum power transfer occurs when RL is equal to RTH. So it's going to be literally the exact same thing here. So if we put these two parts together, we can see that maximum average power transfer occurs when our load impedance ZL is equal to RTH minus J XTH. What is RTH minus J XTH? The conjugate of ZTH. Absolutely right. So in order for maximum average power transfer to occur, our load has to be the complex conjugate of our Thevenin impedance. All right. So I have one in-class assignment problem that I want you guys to work on. Let's work on it for maybe 20 minutes top. Would you mind distributing these to the right side of the classroom? And then after that, we're going to use the remainder of the class as a review for these lines to be on, so I don't do all the way up, it's still on the front of it. Are you going to all the- Absolutely. So what this act is material development. I'm going to say technically yes. What I mean by that very specifically is I'm going to have a problem with guys work that is much easier than the one I'm giving you as an A-class assignment. And it is going to be components. So 100% of your exam will be the material that's already covered based on your homework and all of that kind of stuff that are due before the exam. And then there will be a 5-point bonus problem based on this. No. So I'm going to upload the solutions to the in-class assignments and then that and your homeworks. If you're good on the homeworks, you're good to go. All right. So let's open up something here. So we've got this big growth circuit thing here, and our goal is to figure out what impedance will cause maximum power transfer to happen. And then we need to calculate the maximum, the value of the maximum average power that can be absorbed by the load, okay? So effectively what we're doing is I'm going to put a dashed line down here. And our goal is to find the Thevenin equivalent of everything to the left of that dashed line. So let me redraw what we have. Here's our 4 ∠0 degrees amps current source. Four ohms. ∠0 volts. 2 ohms. Here is our Thevenin voltage. Now I want to make note of something here really quickly. My current source and my voltage source are just phasor voltages and currents. They are not RMS phasor voltages and currents. And how I can see that is because I don't have an RMS anyway, okay? So if we find the Thevenin voltage here and we want to apply it to our power calculations and all of that kind of stuff, we're just going to need to divide the magnitude by square root of 2 to put it in terms of an RMS phasor. Okay, so how might we go about finding our Thevenin voltage for this circuit? So the fact that there's a voltage source and a current source together in the circuit is bothering you. What if it were two voltage sources or two current sources? Mm-hmm. Good. Nothing particularly wrong with that. You could also source transform the 12 angle 0 in series with the 2 ohms into a current source if you wanted to. I think that would actually further complicate things instead of less complicate things. Nick, what's up? Yeah. VTH.
I thought.
Yeah.
We could see the. Go off for you. The 2 ohms. Then I'll be a VTA, which is then in series with that 6 ohm. Then we'll have here at that.
Looking for a voltage drop across those open circuited set of terms.
It's parallel 4. This going across.
So we could do mesh. I think personally that, so if we did mesh, I can see of 3 mesh currents right now. Let me just look at as far as nodal analysis is going to go. So I see one big node at the top, 2, 3. Yeah, okay, I guess mesh will be arguably easier, but let's make it even easier by using Trilon's suggestion of doing a source transformation, because that's going to eliminate one of these meshes. Okay. So I'm going to do a source transformation on the 4 angle 0 degrees amp current source in parallel with the 4 ohm resistor. You guys are familiar with source transformations because one of you guys suggested it. How do we do it? So whenever I have a current source in parallel, I'm going to wind up getting a voltage source in series. Hey, just for shits and giggles here. You see how we have this Thevenin equivalent circuit where we have a voltage source in series with a resistance, and then down here where we have this Norton equivalent circuit where we have a current source in parallel with a resistance? Those are the rules for your source transformations because they are electrically equivalent to each other. And the rule for converting is literally this Ohm's law relationship right here, all of which we covered today. So going back over here, that is the wrong thing. That 4 angle 0 amps is going to turn into a voltage source. The 4 ohm resistor is now going to be connected in series. And because V is equal to I times R, so 4 angle 0 times 4 ohms is going to look like 16 angle 0 degrees volts. So making that simplification gives us a circuit that only contains 2 mesh currents. So if I did KVL around mesh 1, I would have negative 16 angle 0 degrees volts plus 4 ohms I1 minus 12 angle 0 degrees volts. This is all the same line. 2 ohms I1 means we're dealing with phasors. It's the same notation I've been using for 2 weeks at this point. The tilde is an RMS phasor, the bar is just a phasor. Negative J4 ohms times I1 minus I2 is equal to 0. Anybody have any problem with that? So that's just me following mesh current I1 around its clockwise path. All right. So now let's look at KVL at mesh 2. Somebody help me out with this one, please. So I like to start at the bottom left-hand corner and then just follow my mesh current around its clockwise path. So what's the first thing that we're going to see if we start at the bottom left-hand corner? Negative J4 ohms, absolutely right. What's the total current flowing through it when we're following I2 around? I2 minus I1, absolutely. And then what else are we going to have? So positive J4 times I2 plus 2 ohms times I2 is equal to 0. Now let's talk about how we might find VTH. So I would argue that we could find VTH by doing Kirchhoff's voltage law around, actually, I need to keep on trucking. This outside path would probably be the easiest one to do, okay? So I'm going to have negative VTH. So what's the voltage drop across that 6 ohm resistor going to be? Zero. Why is it zero? You're correct, but explain why. Right, there's no current flowing through it because it's an open circuit. So if there's no current flowing through the 6 ohm resistor, there can't be a voltage drop across it. So the 6 ohm resistor doesn't contribute anything. Absolutely correct. Okay. So what's the next thing we see? Well, the 4 ohm resistor. What's the current flowing from right to left through the 4 ohm resistor?
No,
Correct. Negative I1. Absolutely correct, Sam. Then we would have plus 16 angle 0 degrees volts. And then we have the 2 ohm resistor. What's the current flowing from left to right through the 2 ohm resistor? It's just I2, but is it positive I2 or negative I2? Negative I2, because positive I2 is flowing from right to left, negative I2 is flowing from left to right. So I'm just following the direction of that green arrow. So negative I2, set that equal to 0. So we could throw all that into our computer algebra tool like MathCAD or whatever to solve for VTH, right? 3 equations, 3 unknowns. Okay, so I'll leave that for you guys to do. Now, let's take a look at how we're going to find the resistance. So I'm going to start with something that I know is not going to work. Okay? And what I know is not going to work is a direct analysis of this thing. So if we looked at a dead network, my voltage source would be off. Here's my 4 ohm resistor. This voltage source would be off, so I have my 2 ohm resistor. I just went counterclockwise on that one because that way I could just easily move VTH to the other side of the equal sign and say VTH is equal to all of that crap. I could have just as easily written it the other direction. The computer doesn't care. All right, so what's the problem with this network? Why can't we just do simple impedance combination here? So the parallel thing isn't in parallel because of that 2 ohm resistor down there, right? So we can't say that the minus J4 is in parallel with the positive J4. So there's no way to combine those. This 2 right here isn't in parallel with this 4 because how things are broken up. We actually have run into an issue where we would need to, if we wanted to do this directly, we would need to do something what's called a delta Y transformation. I understand that you guys probably haven't learned that yet. That's perfectly acceptable. We are going to learn it when we get into 3-phase power, which is our next module, because that's going to be our bread and butter, is converting between deltas and Ys to make our circuit analysis easier. For now, since we don't know it, and I don't want to spend half an hour explaining it to you yet, we are going to choose an alternate route, okay? So instead of finding ZTH directly, what we're going to do is we're going to find I Norton, because if we have I Norton and we have VTH, the ratio of those two things is our Thevenin voltage, right? So let's put that 16 angle 0 degrees volt source back here. So how do I find the Norton current again? Nope. Short the terminals, absolutely right. So short circuit these terminals, find the current flowing through the short circuit. Let me move it to the inside here. So how might we go about doing that? Mesh, why not? So it's going to be incredibly similar to our first analysis. So here's our current I1, I2, and I3. But now, since that right-hand side is short-circuited, I3 is not going to effectively just be 0, right? So we would do our analysis from here using mesh analysis, find I Norton. The ratio of V Thevenin to I Norton gives us the Z Thevenin, and then it's literally just using equations. Mm-hmm. So let's pop back over here. Let's look. Actually, let's scroll down. We're looking at this expression right here. So for all of the impedance stuff, like calculating ZTH, it will not matter at all. However, for our power relationship, it will. And the reason it will is because right here, we have the magnitude of our RMS phasor Thevenin voltage squared. So realistically, if we left it in terms, let me do something down here, right? This is an aside thing. So a couple of things here. Let's prove some stuff out just really quickly. So V Thevenin is just this V Thevenin over the square root of 2. And I Norton as an RMS phasor is just I Norton over square root of 2. Our Thevenin impedance, Z Thevenin, is the ratio of V Thevenin to I Thevenin, excuse me, I Norton, which is V Thevenin over square root of 2 divided by I Norton over the square root of 2. And we can see very easily that that square root of 2 and that square root of 2 cancel each other. So finding Z Thevenin, it literally doesn't matter if we use the RMS phasor voltages and currents or the phasor voltages and currents. The ratio is going to be the same either way. Okay. Now for our power relationship, we have the magnitude of V Thevenin squared, right? Which is just going to be the magnitude of V Thevenin over the square root of 2 squared, or just 1/2 time for the projector to reset. Yes, it's getting progressively later by a couple of minutes every day, which means by the end of the quarter, it'll be the class after us's problem. All right. Yeah, I don't know what the deal is. Huh. Now my screen over here is blinking as if it's trying to, oh, I think it finally decided to do it, maybe. All right. So anyway, long story short, realistically, you could just keep it as a phasor voltage and then multiply by 1/2 and you'll get the same result. Because you're just multiplying by 1 over the square root of 2 squared. So anyway. All right. So I have talked you through things. We've got about 30 minutes left, so let's review. What do you guys feel uncomfortable with? Okay, so let's look at, do you have a specific problem you want to look at, or just do you want me to make one up? I have no problem talking about homework assignments and all of that kind of stuff. If you feel like that would be more useful, I can definitely just make shit up and we can look at that too.
If you could do, it was homework 3, number 1, and we decided to try and attack it with middle.
Okay, so
Hard. Just to make it easy. Alter the.
let's see, so 280.
Usually the homework 3, number 1. And it was much easier to do it with that. Was it for 2? Like, we did number 1 with math, and I was like, what if we tried that?
Is this the one that you want to do with nodal, or do you want to do this one, or this one, or literally any of them? It doesn't matter. We can throw nodal at any of these and it'll be okay.
We could look at run number 3 for the LP and the OC.
My concern is that you think it matters what the circuit looks like. Because it doesn't. Like, if you're comfortable with the analysis techniques, what it looks like is completely and utterly immaterial. Mhm. So let's find out, okay? So let's work this problem using nodal analysis. Okay. I have the memory of a goldfish, so now I have to immediately go back. So 4 ohm. I'm just going to set things up because, you know, that's what computers are for solving things. And I'm just going to draw it in the frequency domain from the jump because I want to. Capacitor over here. All right, so let's see here. So 12 angle 0 for the voltage source. And 2 angle 0 degrees amps for the current source. All right, so let me throw this into my calculator really quickly. So I'm figuring out the impedance of the inductor. So that's omega is 100 radians per second times 0.04. Looks like J4 to me. This is phasor voltage Vy. And now the 1 millifarad capacitor, 1 over 100 times 0.001 is J10, or negative J10, excuse me. So that's what my circuit looks like in the frequency domain. So you had a question about how many nodes there are. So I'm going to show you how I identify nodes. So what I like to do is I start at one element, and then I just follow the wires along until I hit another element. And I just keep on going. So I have that one node on top that I've labeled in red. I've got a node right here. I've got a node right here. I've got a node right here. And I've got a node down here. So I have 5 nodes, one of which will be my reference. So it looks like I'm either going to have 4 nodes or 4 meshes that I have to solve for. So realistically, this problem is equally difficult as a nodal problem or a mesh problem. It might look slightly more intimidating as a nodal problem, but the size of the system is the same. So now let's talk about ground. I'm going to choose to put ground at the bottom node, the negative polarity terminal of that voltage source. Whenever I have a problem that I'm doing nodal analysis on, I always choose to put my ground or reference node at a node that's touching the most voltage sources, because there's only one voltage source here. That seems like the most obvious choice. I might revisit this after we set this up with what it would look like if we chose ground at a different node, just so that you guys can kind of see what shakes out of that. Okay. So bottom node is my reference node, so now I need to assign nodal voltages to my other 4 nodes. So let's just say that this one on top is VA. This one over here is VB. This one right here is VC. This one right here is VD. Anybody got any questions, comments, or concerns thus far? So just as a heads up, I'm gonna actually label the steps that I'm doing because I do this the same way every single time. Okay. So first thing I do is identify my nodes. The next thing I do is assign ground. Third thing I do is assign nodal voltages. So what I'm going to do now is I'm going to write voltage relationship equation for each voltage source. So I only have one voltage source. So what's my voltage relationship equation going to be? So I just find the voltage source. I write down what the voltage source is telling me, 12 angle 0 in this case. The nodal voltage at the positive polarity terminal of the voltage source is VC. The nodal voltage at the negative polarity terminal of the voltage source is ground or 0. So I have 12 angle 0 is equal to VC. All right. So now I'm going to write my KCL equations. Okay. So actually, let me backtrack here very, very slightly. Okay. I think I've mentioned this to you guys, but I'm not 100% sure, so I want to talk about it really quickly. Every time that we have a voltage source, we have what's called a supernode. And that supernode is just between the 2 nodes that the voltage source is touching. Whenever our supernode contains ground, we don't need to write a KCL equation for that supernode. So the only thing we're going to have is that voltage relationship equation, and we're good. We can't write KCL at node C because there's no way for us to express the current that's flowing down through that voltage source in terms of our nodal voltages. It's literally impossible, okay? So we have all of the information that we need for node C, so we're just going to move along. So if there was a resistor there instead of the voltage source, we would have VC divided by the resistor value, like every other resistor impedance or whatever. No, so when you're saying if there was a resistor there, let me just, okay, good question. So what you're suggesting is actually something like this. Okay. So realistically, we would actually have another node there that would have its own nodal voltage and all of that kind of good stuff. Right. Yep. So anywhere there's a point of interconnection between 2 or more circuit elements, there's a node. So we have to identify every single one of them. Those are very easy to overlook, but they're still a node because they still represent a point of interconnection between circuit elements. Yeah, and so we would have a VE right here. And so we would actually have VE is equal to 12. And then we would be doing KCL at node C. So let's get rid of that stuff and go back to the specifics for this problem. Okay, so now we're going to write a KVL equation, or excuse me, KCL equation at A. So here's my step 5. Write a KCL equation for all supernodes that don't contain ground. For our circuit, there are literally none of those, so we're going to skip that step. And then step 6 is to write a KCL equation for all remaining nodes. So starting at A, I'm going to be doing this current plus this current plus this current. I always write my KCL equations with the for nodal analysis with the current leaving my node of interest. And the reason why I write them that way is because we'll see that our VA term will always be positive. So this is just my way of making sure I don't have a whole bunch of extra negative signs there to confuse me, because I personally know that I am bad at keeping track of too many negative signs. So what's the current flowing down through the 4 ohm resistor going to look like? I disagree, because it's not flowing to ground. So VA minus VB over 4 ohms. Absolutely right. So just to remind you guys, the node where the current starts minus the node the current is flowing to divided by the impedance, okay? Anytime we have an impedance, that's the rule. So what about the current flowing down through the J4 ohm inductance? Yep. And lastly, the current flowing down through the minus J10 ohm resistor. So VA minus VD over minus J10 ohms. All right. Those are all 3 of the currents. I have 3 terms, so I set it equal to 0, go on about my business. So now we're going to do KCL at B. So we're going to have this current up, this current to the right, and this current down. So what's the current flowing up through the 4 ohm resistor going to look like? VB minus VA over 4 ohms. Absolutely right. What's the current flowing to the right through the current source? To angle 0. What's the current flowing down through the 7 ohm resistor? Yeah, so VB minus 0, which is the same thing as VB, over 7. Absolutely correct. Okay, so we had 3 currents, so we're good to go. Like I said earlier, we're going to skip node C for our KCL expressions, because number 5 right here says we write a KCL for all supernodes that don't contain ground. This supernode does. So we skip that one. And lastly, we're going to write our KCL expression at D. So at D, we are going to have this guy up, this guy to the left, and this guy down. So what's the current flowing up through the minus J10 ohm capacitance going to look like? So VD minus VA over negative J10. Absolutely. The current flowing to the left, oh goodness gracious, through the 3 ohm resistor. Yep. And lastly, all right. So we didn't do step number 5 because step number 5 tells us to write the KCL expression for all supernodes that don't contain ground. So let me rehash some things real quick, and then we'll work a problem where we don't get to skip that one in just a second. Okay? So anytime that we have a voltage source, we are going to have a supernode. And that's just us effectively drawing a bubble around our voltage source, okay? So in this case, our supernode would be between node C and ground. Because our supernode contains ground, we don't write a KCL equation. Okay? The reason why we don't write a KCL equation is because there's no way for us to figure out what that current is flowing down through that voltage source in terms of our nodal voltage, right? Whenever we have an impedance, it's easy because it's just, you know, the voltage where it starts minus, the voltage at the node where the current starts minus the voltage at the node where the current ends divided by the impedance. Whenever we have a current source, it's also easy because it's just whatever the current source is pushing, up or down. With a voltage source, the current that's flowing through it is just whatever the hell it needs to be to make the circuit work. There's really no way that we can relate it specifically to the nodal voltages, so we just avoid it. And we already have all of the information that we need from that node because we said, well, 12 angle 0 is just VC. There's really no need to have any more information. Okay. So now that we've set up our system of equations, right? We could solve this system of 4 equations using our computer. Now we need to figure out what Ix is and what Vy is. So let's do that over here, okay? So how would we express Ix in terms of our nodal voltages? Well, Ix is the current that's flowing down through the J4 ohm impedance. So what's it going to be? We literally already wrote this expression. So what's the node the current starts at? What's the node the current flows to? VC. So VA minus VC over J4 ohms. Literally this exact same thing right there. I disagree. Let me tell you why I disagree. So I'm not trying to pick on you. Trilin suggested that the quantity Vy would be Vd over 8. Exactly right. Vd over 8 ohms is a current because voltage divided by resistance is current. Current is not voltage. I want the voltage. So what's the voltage at the positive polarity terminal of Vy? Vd. What's the voltage at the, my screen keeps moving on me. What's the voltage at the negative polarity terminal of Vy? 0 or ground. So anytime we're looking for a voltage, it's always just nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal. It is never not that. So this is how you would solve that particular problem using nodal analysis. Let's look at problem number 2 from that homework set, where we've got that voltage source in an odd position, and I'm going to choose ground to be just at the bottom. Um, I'm about to say something and I don't mean it to be super rude, but you were doing your mesh wrong then. Because for better or for worse, every single one of these problems could be solved using either nodal or mesh. Okay. Realistically, you could solve every problem using both methods. And if you get the same answer both times, then you have done it correctly. If you get different answers, then that means that either your nodal analysis is incorrect or your mesh analysis is incorrect. Because I give you the answers, it's pretty easy to see which one of those analysis methods you made a mistake on. So I'm happy to help you sort that out, but we've got 13 minutes left and I want to cover something else here real quick. So let's look at this guy right here really quickly. Oh, dang it. Getting flustered trying to do this too quickly. All right, so I'm going to run through and I'm going to calculate my impedances really quickly here. So let's do like the 1 Henry. So that's going to be 8 times 1. So that's going to be J8, which makes this guy up here J16. Then I have 50 millifarads. So that was going to be 1 over 8 times 0.05. So 2.5. So that's 5 halves. And then 1 over 8 times 0.2, I think, is 5/8. And then let's see, so this is 40 angle 0. And here's Bx. Here's Iy. Okay, so before I even start with my nodal analysis steps, I'm going to do a couple of things here to simplify this circuit, okay? So what I mean by that specifically is anywhere that I have elements in series, I'm going to lump them all together as a single impedance. So 5 in series with J8 is going to look like 5 plus J8 ohms. Exactly right. I do that to eliminate nodes. This guy over here on the right-hand side is going to look like 3 minus J5/8. As long as they're in series, doesn't matter. I could, so if I could replace that 5 plus J8s, or I can observe that that 5 plus J8s is in parallel with 3 minus J5/8. That being said, the current IY is the current flowing through that 3 minus J to the 5/8. And so if I lump those together, that current IY goes away. So I wouldn't do it any further than here for this particular problem. I would absolutely lump them together. So let's see. So J16 minus 5 halves. So let's see. 16 minus 2.5 is 13 and a half. 13 and a half. 27 over 2. So 6 plus 27 over 2 for this branch over here. All right. So my circuit is as simplified as it could be. Now I'm going to identify my nodes. So we've got this guy right here. This guy on bottom. This guy over here. This guy right here. I am choosing my ground to be the bottommost node. This is going to be node A, B, and C. And I now have a supernode between nodes A and C, not connected to ground, very explicitly not connected to ground so that we see what we need to do here, okay? So the first thing that I'm going to do is I'm going to write my voltage relationship equation. So 40 angle 0 degrees volts is equal to VA minus VC, just the nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal, which is how we write any equation looking for a voltage. Okay. Now, that's step 5, write a KCL equation for all supernodes that don't contain ground. So what we're going to be doing is we're just going to be looking for the currents that leave our supernode. So let me do these in this light blue. So I have this current flowing out of my supernode. I have that current flowing out of my supernode. And I have that current flowing out of my supernode. Okay. I'm going to add those three together. Now I want to show you guys something. Okay. And it's effectively the reason why this works. So if I did KCL at node A, I would have the current flowing to the left through the 6 plus J27 over 2, the current flowing to the right through the 2 ohm resistor, and I would also have this current that I've labeled in gray flowing down through the voltage source, which I can't express. When I do KCL at node C, I would have the current flowing up through the voltage source, as well as the current flowing down. If I add those two KCL equations together, the two currents that I've labeled in gray cancel each other out because they're the exact same current, but they're flowing in opposite directions. Why can I add two KCL expressions together? Because 0 plus 0 is always equal to 0. So this is just a shorthand way of lumping all of that analysis into a single expression. Okay. So our KCL equation would look like VA over 6 plus J 27 halves plus VA minus VB over 2 plus VC over 4 is equal to 0. Now we would be on to step 6, which was just write KCL equations for all of our remaining nodes, which in this case, the only one we have left is B, right? So KCL at B would be VB minus VA over 2 ohms. Plus VB over 5 plus J8. Plus VB over 3 minus J5/8. Three equations, three unknowns, use the computer to solve. So what's Vx going to be in terms of our nodal voltages? VC done. what is IY going to be in terms of our nodal voltage? Absolutely. So that's how you would do that problem using nodal. I get that mesh is something that you guys are more comfortable with. So I just want to, I hesitate to say the word warn you. But I've already told you that I might give you problems like this where I'm asking you explicitly just to set things up, not to solve it because you won't have a computer in front of you or anything like that. Seeing how uncomfortable you guys are with nodal analysis, I guarantee you I'm going to ask you to set something up using nodal analysis. I'm also going to ask you to set something up using mesh, but I am explicitly going to do it. I might go so far as to label all of your nodes and all of that kind of stuff for you so that there is a single finite solution so that you don't drive my graders up the damn walls. But yeah. All right. So I'm going to upload my solutions to all of the in-class assignments. And then that plus your homework is all of the studying you could possibly do. All right. You guys have a good rest of your day. I will see you on Thursday for your test. My office hours don't start until 1:30, so. Oh, so just as a heads up, if it's several of you guys coming, and I'm totally okay with that, we will probably just go downstairs and find a room at 2 o'clock. I already have Neptune Hall, room 105 reserved.